Thank you for the invitation, and actually I'm not sure I should thank the speakers, the committee, for the invitation, especially since they put me as a first speaker. So I don't know because, so first of all references can be found on the website. So because the problem is I have nothing to say. I have nothing to say because some years ago, I mean 20 years ago, there was a wonderful, an extra copy of the Bulletin de la Société Mathématique de France about René Thom. And you will see that the many wonderful papers, including a paper by, some papers by Thom himself, and Hommage à René Thom from Ivar Ekeland. And all I had to say, I said at that paper. And I'm sure that you have other people recorded. Remember, here you have, I saw a paper by Dennis Sullivan, René Thom, and so on. So this was done. And now, so what do we do? So I find myself in the situation of Mark Antony. Remember Mark Antony? You have this most famous quotation in the English language: "Friends, Romans, countrymen, lend me your ear. I come to bury Caesar, not to praise him." So my situation is even worse than the situation of Mark Antony, because I'm not going to praise René Thom. This has been done. And as for burying him, he's been buried 20 years ago. So what do we do? Well, Thom is buried. I'm not going to praise him. So let's talk about today's problem, the problems of today. Don't talk about the dead. Don't praise. Let's think, what are our big problems today? Now, as far as I'm concerned, the main problem today is climate change. You know, it overshadows, and again, another quotation. For another quotation, remember, as far as I'm concerned, we're walking in the valley of the shadow of death. This is, I think, Psalm 22 or 27. And in the situation we are now, I don't even think it's interesting to worry about Riemann's conjecture. So this is a major problem, and I think it's underestimated. And so for 20 years now, we've been trying to understand this problem, and you start by what you are familiar with. I'm familiar with the economics of climate change. Now, if you go into the economics of climate change, you get good news, very good news, actually. You shouldn't worry. So there was a Nobel Prize in economics. William Nordhaus, Yale, in 2018, he got the Nobel Prize because of his work on climate change. And these are his slides. I encourage you to go on the net and find Robert Nordhaus slides on climate change. You're all hearing me? Everything's working? So these are his slides. Talk at Stockholm, Nobel Lecture in Economic Sciences. So here, I'm not going to put all his slides. I'm going to put the first ones. So, and this, you know, what's interesting now is this. You see, there are some math. He's maximizing something. The mathematical dice model, this is what he's doing. So he's maximizing something. So we are in math optimization. He's maximizing W, which is W, it is welfare. So he's maximizing welfare. And he maximized an integral from 0 to infinity, t time, because he's looking at the Earth from now to infinity. Sorry. And he's maximizing something. C is consumption. Think of it as GDP. U is utility. And here you have this thing I'm going to talk about, e to the minus RT, which is a discount factor. So what he's saying, I'm looking at GDP 20 years from now. It's going to give me a certain amount of utility. And since 20 years from now, it's not as much as it was today. It is in 20 years. So I'm going to affect it to the factor, which is the interest rate. Clear to everyone? So it's maximizing. You have a math problem. And subject to, there are some dynamics. GDP depends on a lot of things. So he has this problem. And then here it is. And lo and behold, there is an optimal solution. Well, you have nasty things. You have all these ecologists, Greenpeace and so on, who want to keep global temperature beneath 2 degrees. You see this guy, it's possible. This is it. But we optimize. And if we optimize, we are lucky to find an optimal solution. Here it is. And in 2100, the optimal solution gives you 3 degrees 0.5. So 3 degrees 0.5 is optimal. The math is wonderful. This is what it gives. I know of no scientist in any field other than economics who says that anything beyond 2 degrees is less than catastrophic. This is a Nobel Prize in economics. You know? So, why? So let's look into that. So this is, I'm going to investigate this question, and now let's go into the math. So as I told you, what are these guys, what are they doing? They're maximizing U of C of t. So we have a discount factor. It happened to be e to the minus RT, but in fact, it's just saying that if you get something good in 20 years, it's worse than if you get it in 10 years and worse than you get it today. So you put a discount factor that has to be R0 is 1. Yeah, if I get it today, I get it today, and then it's decreasing. No reason should be to the minus 30. And then you have some dynamics. The dynamics in the classical model, the one he's using, basically is the famous one, is the following one. C is consumption. I'm consuming. U is the utility of consumption. Who consumes? Well, there's a representative consumer, one guy. Or it's a mean consumption, as you wish. Who maximizes? You have someone who decides. There is a benevolent dictator. I'm not joking. These are the economics of climate change, and these guys decide our future. And the dynamics, they're meant to consume. You have to produce, of course. How do you produce? Well, you produce with capital. But capital, so think of capital and consumption being the same. Think of corn. So corn, I have the corn crop today. I can eat some of it and I can resow some. That's investment. So f of k is how much corn you get. But you get if you replant how much. So this is basically testing that investment equals production minus consumption. And this is positive. And you have all these functions u and f, and they have to be concave and standard specification. U of c, that should be 1 over alpha t to the alpha. Here I have a mistake. F of k is 1 over beta k to the beta, beta less than 1. And so this is the basic problem. Economic interpretation, as I told you, there is single good in the economy. It's corn, if you want to understand, and then they say it's GDP. You have a production function. There is a representative consumer. You maximize utility of the representative consumer of the time. And the economy is run by a benevolent dictator, which seeks to maximize the welfare of a representative consumer over her lifetime. And you have here this thing, which is going to be the subject of my talk. Clear to everyone? Good. So, first of all, sorry?
There is a problem of sound. So, Clément?
No, maybe. Do you have a phone?
Yeah.
Could you remove it? Let's try.
Let's try. Okay. So, anyway.
Just a question. Her lifetime. Who is she? Dictator or consumer?
The dictator.
No, just her lifetime.
His lifetime. His lifetime.
His, okay.
No. The dictator is a man, as usual. Oh, shit, what am I doing? Yeah, the dictator is a man, as usual. I don't know what I wrote. So, and the consumer is so the dictator maximizes utility of the representative consumer over time. Period. Okay, so I mean, you get a very, so now the discount factor. So all this goes back to Frank RAMSEY. Frank RAMSEY, 1928, talks with Keynes and sets out this model, and he says R is 1. There's no reason to discount future generation. If you do that, you are unjust, unfair, and it's stupid. So RAMSEY takes r of t equals on, and it takes strong objection against putting r of t less than 1. There's no reason to discount future generations. Immediately after, the economists come in and say, of course, we should discount future generations, and they put in e to the minus rt, and this is the classical theory of economic growth. And more recently, psychologists and others have say, well, they do experiment, and they say, well, why should it be e to the minus rt? But let's concentrate on this e to the minus rt, and this is a neoclassical growth model. You maximize e to the minus delta t u of c dt under constraints right here. So what you have here is a very simple problem in one dimension of the calculus variation. You could have given it to Euler. Euler would have found the solution. Very simple, one-dimensional, but that's what people do. And when you do it, you find with certain specifications. Now, it has some nice properties, not as obvious as it looks, because it's not a Boltzmann problem. The end point is free. And the end point is free, and you go to infinity. So yeah, there's certain difficulties, but the solution is obvious. It's not obvious, it goes that way. So this is time. This is k of t. And you have a k infinity here. And whatever the starting point, and this is the equilibrium growth of John von Neumann. So this is macroeconomics 101. Okay, and this is basically the Nordhaus-Dice model, and this is the characterization of the equilibrium point. Now, discussion. Now, this problem, however, this specification here has an extremely nice feature. What's e to the minus delta good for? Well, there is time consistency, because look at what happens. At time 0, so look at what happens. Here is time, and here's a flow consumption. And the guy who is here wants to maximize integral from 0 to infinity of u of ct e to the minus rt dt. And the other guy goes to maximize sum from 0 to sum from. And if you start again at time t, so you see what happens. I start here. The benevolent dictator say, well, we start here, we do this. But the benevolent dictator, 2 years later, he may reconsider and say, am I still on the right path? Or a government may do that. And he's not going to look at that. He's going to look at sum from t to infinity, e to the minus delta, not t, but t minus t, because he starts from time t. Bygones are bygones. And that is e to the minus, I'm sure I made a mistake somewhere, but I'm customary of the fact, and this should be e to the minus delta t, sum from 0 to infinity of u of ct. I see, excuse me. I forgot, yeah. I should never make computations. And so he's going to do that. That's from time t. So he's looking at that from time t. But this small piece looked at from time 0 will be sum from t to infinity of e to the minus delta t u of c dt. So that from time t, 0 and from time t. In other words, this little piece, you can evaluate it from here, and you can evaluate from here, and the difference is very clear. You get out, it's the same thing, e to the minus rt. It's a kind of quasi-variance. And this is very nice, because if I'm here, and I compare, if I'm here, and this is C1, and I can compare two paths, C1 and C2, if I decide at time 0 that this is better than that, when I'm here, I will still say this one is better than that. So this is a kind of time consistency. If I say that a path is optimal now, when I arrive at time t, I look again, I say, yes, it's still optimal. But you see, it's a property of the exponential. So how general is exponential discounting? Psychologically, it's a joke. People discount, but they much prefer, anything as far as they're concerned, anything that's between 5 and 10 and 100 years from now is the same for us. However, tomorrow and in 1 week is a big difference. So psychologists say, no, that's a good one. Now I've been working on intergenerational equity. Intergenerational equity, when you're in climate change, is you have maximized for the representative consumer, but there will be more representative consumer. These guys will be born. Take them into account. And if you do that, you end up with things of that kind, which is a combination of exponential. So this is what you're going to work on. A discount factor, which is a combination of exponential. So if you do that, you have time inconsistency, meaning that you are in a situation where at time t equals 0, I decide this is optimal. This is optimal from time 0. And when I reach time t, I'm still the same dictator. I say, well, this is stupid. This is optimal. Optimization is meaningless. It's meaningless because what the guy at time t 0 is going to do, he acts as if he's going to do that at time t. But at time t, he's going to do something completely different. Optimization is worse than, optimization is totally meaningless. But we're mathematicians, and already that's one big critique of the Nordhaus model, who optimizes, and y is et to the minus rt, and the whole thing collapses down. I'm not going to go further into that. But we're mathematicians, so we want to do something more. So we're mathematicians, so let's do some mathematical work. Optimization cannot work. Mathematically it works very well. You can put the optimization point times 0. You have Euler-Lagrange and so on, but it's just not implementable. So what could we put instead? So I'm not going to that. We're going to look into a new kind of solution, which is, how can I say, which is a kind of Nash solution. I had the word, but I forgot it. We're going to look at something else, namely, how can I say, something all generations can agree on. We are going to ask is there some kind of feedback? A feedback means you substitute in the dynamics C from sigma of k. You substitute that in the dynamics. So that's a feedback. Is it possible to devise a feedback such that at time t, so we are going to at time t, I look at the feedback, and what do I know? I know that all future generations will apply the feedback. So, and now I look what is optimal for me now, and it turns out that what is optimal for me is to apply the feedback as well. This is what is called an equilibrium solution, a Nash equilibrium. And you see it's a solution where it's a policy which each generation has its own incentive to follow, provided all the other generations do the same. Classical in game theory, unilateral deviations are proscribed. Now the difference with the preceding situation is that each generation has power only during its lifetime, which is a small period of time. So you have all these people coming in. Each one has power doing, or think of governments. Governments have power during 1 year, and there is a policy. They know the policy is, they assume the policy is going to be followed by future governments. What do we do today? Well, it's best for us to apply the same policy. So this is a new definition, and I'm interested about the math. And here we get, yes, one thing I should say. I am now assuming this specification. So this specification, you get a very complicated, you get a Hamilton-Jacobi equation. Because of this specification, the whole system reduces to 2 equations. So it is for this specification. And now, this is typically the topic of my talk, we get, if you work this out, do they exist? You get this, and you get a system of 2 equations, and you see the 2 equations are there. I've singled out that one because the important one. You see that these 2 equations are connected by this AV, connected by this BW. I mean, if you didn't have B, then this would be a single equation with certain boundary conditions, and they give you the feedback, and the solutions have to be smooth. Easy. So I see a system, 2 ordinary differential equations from 0 to infinity, fine. Try to understand this, and just to make matters simple, this important one, I'm going to take b equals 0. B equals 0 means that I go back to the exponential case. So let's just to understand the problem, take b equals 0. And if you take b equals 0, you get this equation, one equation with one boundary condition. And here you see a new u tilde appear. Let me write down here for future reference. You have a new function u which appears, which is defined as follows: u tilde of y equals max of u max over x of u of x minus xy. And you have, so this is, this function u is concave, which is really 1 over alpha x to the alpha, as I remember. So this function here is convex. So this is how it appears. It's 1 over a. And you have the yoga of duality. The yoga of duality, which I understand in terms of convex analysis, which goes back to la transformation par polaire réciproque. It goes back to Sophus-Lee and so on. There's a yoga of duality. U is dual to u tilde, but u tilde is also dual to u, so that you have u of x is the minimum of over y of u tilde of y plus xy. And you can even say when it is attained at y equals u prime of x, and this is attained at x equals minus u tilde prime of y. Okay, so now what we have here, we have a very well-defined equation in, and the function which is looked for is v of k. So, standard. What's the problem here? The problem is here, u tilde v prime. The problem is it's in implicit form. It is in implicit form. You see that v prime is here. It's not solved with respect to v prime. So there may be several solutions. No big deal, right? No big deal. It's an implicit differential equation. So let's write that more. So you have to solve u tilde v prime plus v prime f of k equals v. And now here is a picture I want you to look at. Which is basically the crux of my talk. So here is the picture now. So here is v prime. Here is the function u tilde of v prime plus f of k v prime, and here is rho v. And we want to solve this. Rho v equals u tilde v prime plus v prime f of k. And you see immediately, here you have two solutions, here you have one solution, and here you have zero solution. Okay? And you can put exactly, because of yoga, you can put things directly here. So the interesting point is here. Because of the yoga, you find that here, this is u of f of k. Here is k, excuse me. Here is here is v prime. Here is v prime, yes. This is u of f of k, and the solution. This is u of f of k, and here you have v prime equal u prime of f of k. This enables you to write the phase space. Here is the phase space. So you have k here. Here you have the function u of f of k equal v. And this is the phase space. And the equation here, if you take a point here, and then you have to solve the equation here. And so if you are in this region, no solution. And if you have here, and if you are here, yeah, I have. Voilà, ça y est. And if you have here, you have two solutions at any point. No big deal, right? Nothing to write home about. You have two solutions, you just extend, no problem. But there is a twist, and so this is what it looks like. Two solutions here, one solution here, which is going to look like this. One here, fine. Now, if you go back, you see that is asked for a smooth solution. And so, let me now complete the phase space. So, the phase space, let me complete the phase space then. Yeah, here it is. This is what it's going to do. This is and you have to make out a smooth solution out of these guys. It's a global problem. It took me some time, so it is by the way, the boundary condition is here. So you have to build a smooth solution extending all over K. And this is, I thought, this is an implicit differential equation. I looked for references. The only reference I could find was in Thom. He wrote about that in his paper on envelope theory. And this is very much in the Thom spirit. You have the rebroussement and so on. And he was basically the only one who really discussed the problem. So you will see, I will complete the phase space. It's an incredibly beautiful object. It's the only reference I could find. And it reminded me of an old saying of Thom. Thom comes back, he will not stay buried, and he used to say, c'est beaucoup trop simple et naturel pour les gens. So let me complete the phase space so that you see what it looks like. So how do you build it? You see, what happens is that this goes down. And you have this. And this. And it goes down there. And you have this. And this. And here, at this point, you see, you have another solution coming in, and the other solution coming there. And this will build two smooth solutions. You see? At this point, the two things coalesce together, and you have two possible smooth solutions. And then by further considerations, you eliminate one of them. And over here, you have things like that. Okay. This requires analysis. So, how can you prove these things? Well, in that particular case, yeah, I still have some time. In that particular case, how do you solve these guys? Well, I'm in a simple case. So, our equation was that what u tilde of p plus f of k v prime was rho v. So you write dv equals p dk, and you get a Pfaff system. This trick, I learned that from François Ludenbach, who learned it from Thom, I think. So you do that, you work. You work, meaning that once you have that, so it's a Pfaff system, and then you consider initial value problem, and then from this equation you can derive dp over dk or dk over dp. And of course, since at this point everything goes back, so you have to derive dk over ds and dp over ds. You blow up the whole thing. In the general case, you see, the general case is worse, because now you have this system which is coupled. The phase space now is no longer kv, it's kvw. And the boundary now of the phase space is going to look like that. You are going to have, I'm no chancinaire. You see, I just, it's going to be like that. K, V, W. And in that space, you're going to have a barrier. And you're going to have the same kind of thing, nothing on one side, two on the other side of the barrier, and you have a small segment of contact, no longer a point, but you're going to have a small line of contact. Anyway, it's one dimension more. And so now you have to be clever. You have to introduce, to blow up, so introduce a suitable variable. You have a Pfaff system again, or 3, and then you do some linearization. But it's the only time in my life I had to apply the central manifold theorem, because two of the eigenvalues vanish. Equilibrium strategy, meaning it's not complete, it's not trivial. And this is what you get. You go back to this problem. This is a problem we're treating. There are optimal solutions, one for each starting point, but have mathematically no meaning. But there is an equilibrium solution. One for each starting point, but have mathematically no meaning. But which are all going to look the same as the one I described. So they're all going to look like that. So that is T, that is K, so they're all going to look like that. And here you have a K infinity, but the K infinity has to lie. You can choose any K infinity between this and that. In other words, we can all write down a contract. So the we can all write down a contract will converge to some K infinity. for any k infinity going to a k log and a k bar. So typically, if you're interested in conservation and k is nature, you would like to choose a k high which is as high as possible. But just to say that optimization is meaningless, you can try to do other things. So, you see, this was, we thought we buried Thom, but it is not really clear. Not really clear. He comes up and you see the thing through his eyes. So are we finished with that? Well, you see, climate change goes much farther than some mathematical models. So what's the next thing about climate change? The physics. I understand the economics. I don't understand the physics, and much less the biology. So what about the physics? So let me show you something which is not at all a scientific paper. I put it on the web. You can find 10,000. You can have, you see, Met Office. I don't even know what Met Office is. Fact sheet of December 19. Risk management of climate thresholds and feedbacks. They're talking about AMOC. Atlantic Meridional Overturning Circulation. So what is AMOC? AMOC is this. So what is AMOC? The water, this is the water, there is one ocean on this planet. There are not several oceans, there's one. And the water of the ocean circulates. It's not, don't imagine it's just a pool of stagnant water. It moves. It's important that it moves for two reasons. One, that everyone knows it brings it brings hot water and so on, the current. And the other one is it keeps life in the ocean. Because if the water is not moving, there will be no oxygen downstairs. And all these guys are going to die. So this is the global circulation of the ocean. And you see how it works. You have red is hot water, and you see that the hot water, red is hot water, and hot water, of course, is above. So all the currents you see are warm currents. So it is like an escalator. So you have all, you see, you follow the hot water. This you know very well, is Gulf Stream, which brings hot water from the West Indies to Europe and warms Europe. And then here it sinks and it becomes a cold current that goes back. So very natural, but question, why does it sink? Well, it sinks for small reasons. It sinks because the salinity, because up there, for instance, then many small reasons. One of the reasons being up there, there's fresh water because of all the ice. And the hot water and the fresh water that is pouring in from the glaciers brings down the salinity, and then the whole thing sinks. Very small things. Now, the problem is that this could change. It has changed historically. And what? And you see, the AMOC could weaken and collapse into a status reduced flow with a consequence such as that. So you see, for instance, temperature over here could be lower by 80 degrees in the mean, of course, because all this has a lot of variability. It could be much worse. So the climate, and you see the climate, you see New York is here, Spain is here. So you see major changes. And the problem has changed historically, and this is what they call a tipping point. Now, another reason why economic models are so wrong is they don't take into account the tipping points. So you have several. I'm talking about one. And the report of the IPCC says this is not supposed to happen for the 25th century, but recent papers published in Nature, based on historical data, you know, they look at the data, say this could happen starting in 2050. And it's very likely to happen in this century, with the consequence you see, and consequences, other consequences of the biology. I mean, the fish are just going to die. Okay, so what do the papers say? So remember, this is not a technical paper, fact sheet, and then they try to explain something. They're trying to explain that hysteresis, namely, if the thing falls back, it will stay back. I mean, if the thing stops, you're not going to bring it back. It's just not possible. It is, you go from one stable state to another, and actually people have great difficulty understanding that. I think most economics don't do it, and people just don't. Why don't they? Because it's not well explained. René Thom explained it, and he explained it much better. So here, for instance, you see there is an explanation by René Thom itself of this phenomenon. It's a catastrophe. And here is what he's saying. It is a mathematical theory which, catastrophe theory, it's a mathematical theory which is simple and deep, which explains threshold effects. Take, for instance, mankind. You put mankind at stable equilibrium, and you see that they can move a little bit back and forth, but climate is stable. But now let us move slightly the parameters, that is the shape of this curve. Mankind doesn't understand. The situation around is just the same. You change the salinity. Who cares about the salinity in the North Atlantic? Raise your hand. Okay, so you do that. No one cares. And mankind, you go on. Mankind doesn't realize they're still in stable equilibrium. And they say only what's in the immediate neighborhood. And certainly, a small thing tips the whole thing. And you fall over into a new equilibrium you're not prepared to. And this is definitive. Okay, so that's the explanation of Thom. So you see, Thom is here, still around. I'll give you some references from that. So references here. So this is my comic strip, the thing taken from, which was published 2 years ago about climate. So you can find, if you're interested, you can find it. And I also want to quote this, which is where I learned. I'm sorry, I learned this is in this book, which is a very old book by Breuker. This is where I learned about what is it called, differenzierbare Bildungen. And I conclude, and this is what is taught from it.
Other questions?
Yes. A question about mathematical history. You mentioned, Thom, about the envelope. Yeah. I believe Huygens was, when the beginning of differential calculus was trying to work out the direction of envelopes to go for the Huygens. Yeah. Is there, I'm not familiar with that, is there an affiliation between Huygens?
There is an immediate filiation. First of all, about envelopes themselves. If you read the praise of Thom that I wrote in 2002, you will see that among the many praise I gave to him, I wrote, il ne trouvait pas la théorie des enveloppes ridicule. I mean, I was taught about envelopes when I was in preparatory school, and I mean, there are two beautiful things. One was envelopes, and the other was Hamiltonian systems. And no one gave a damn about that when I was at École Normale. Who cared? Thom was interested. And now, Thom himself, if you read his book, Stabilité structurelle et morphogénèse, he explained that he was always fascinated with what he called the caustiques. The caustiques are, he said, at the time of Huygens, he refers explicitly, people were interested in mathematical optics. But mathematical optics, what people did was this. For the story of their study, what's happening near the center. So there's a focal point here, and then you try to correct the aberrations. And he said what was much more interesting was the actual shape that you say. He said, take, for instance, a cup, a cup of china, put it in there, and see the different shapes it takes. And he was completely fascinated with caustics. He refers explicitly to Huygens, and he said that was much a source of his inspiration. And if you look at stabilité structurelle morphogenèse, you will find beautiful pictures of caustics. So this is a direct filiation which he recognizes explicitly.
I have a remark on the Nordhaus stuff. I think you could have been even much harsher with him, because actually at some point he said that 3.5 degrees by 2100 would be acceptable economically, globally, taking into account price that you would give to environment services, etc. So it's not even bad mathematics in the sense that optimization makes no sense, as you said. It's denying the voice of IPCC and the experts and so on.
Yeah, this is what I showed here. You see, this is his optimal solution. The optimal solution is here, and it leads you to 3.5 or 4.
And where is the yes, okay, yes, that's it. Absolutely. But you should be more explicit in destroying that guy.
Have I been clear? I mean, as far as I'm concerned, this is nothing less than criminal. It's nothing less than criminal, because you see, you know, it's so out of sync with everything, and of course it gives credence to policies applied now and so on. I mean, for me, it's criminal. And we talk about ethics in science and so on. So just and it also and again in my view, the only you know so little about the system. I talked about the physics. The physics are simple, man. You just worry about the concentration. You have 3, 4 numbers, the concentration of gases and so on. That's it. For that, you have equations. The biology is tremendous. So so I think that the only reasonable ways to teach these problems are to put bounds. You don't try to optimize anything. Just put bounds. We're not going to cross that particular threshold. But by the way, Nordhaus is not alone. I mean, mainstream economics just says that.
Okay, so I think we can ask more questions during the coffee break, and we'll proceed to the next talk.
Thank you.